Hello, welcome to physics class. My name is Olujimi Gabriel. This morning we'll be looking at moment of force. But before we go into that, here is the correction for last assignment about a screw jack whose pitch is 2 millimeters. Is used to raise a motor car of mass 900 kilogram through a height of 20.0 centimeter. The length of the tummy bar is 40 centimeter. If the jack is 60% efficient, calculate the velocity ratio, mechanical advantage of the jack, effort required, and work done by the effort. You have to take G equals 10 meter per second square. Now, the first thing is you list out the parameters which you are given. We are given the load in kilogram. You multiply by 10 to give you in Newton. Then the load distance is 20 centimeter. I converted it back to millimeters. Then efficiency is 60% and radius, that is the length of the tummy bar, is 40 centimeter, which I converted back to millimeter. And the pitch is millimeter, 2 millimeter. I want all those units to be in the same unit. Now, from our formula to calculate velocity ratio of a screw jack is equal to 2 pi r all over p. Now, that is pi is given to be 3.1414. Now, 2 times 3.14 times 400 divided by 2. Our answer is 1256. As you can recollect, velocity ratio does not have unit. Now, to calculate the mechanical advantage, we know efficiency equals to MA over VR times 100%. Now, when you make MA, when you bring it out, you have efficiency times velocity ratio divided by 100, which is equals to 60 times 1256 divided by 100. Our answer is 754. As you can see also, mechanical advantage does not have unit. Now, the effort required, MA equals to load all over effort. Cross multiply and bring E out. We have effort equals to load all over mechanical advantage. Now, 9,000 divided by 754. You can see we have 12 Newton. Applying 12 Newton to carry a load of 9,000 Newton. That is that. Now we move to the objective of today's topics. Now, at the end of this chapter, you should be able to explain what is meant by moment of force. Moment of force. Take moment of a given force about any point and show their directions. Explain the condition that must be satisfied if a body is to be kept in equilibrium by the action of parallel forces. Work simple problem on objects kept in equilibrium by a number of forces. Explain what is meant by the center of gravity and identify its position for some regular uniform body. Now, look at this diagram. We have a bicycle wheel. This is the axle, the point where you bolt the wheel, that the wheel is moving around. Now, you can see when you apply force in this direction, you have a turning effect. The same thing applies to a tab. You can see you apply force here and you also apply force here. You have force that are acting in opposite direction, but they are of equal in magnitude. But look at the distance from the force here, the distance from this middle point, which is the axis, to where you are applying force. But because we are applying force on both sides, we have turning effect. Look at the distance. The force is like this, and this is the distance from where you are applying the force and the axis. Now, in the diagram, a turning force is exerted and produces a turning effect about a point. This is the point. This is the point. Here, this is the point. Or along an axis. Such turning effect is called the moment of a force. Now, look at. Two factors are involved in each cases. 1. The magnitude of the force applied. 2. The perpendicular distance of each line of action from the axis or pivot. That is the perpendicular distance. Let's say this is where you are applying your force. Now, the distance between here and here, I mean the axis, we call it perpendicular distance. Example is your door. You can see the door is being pinned down. The door is pinned down along two bolts here. When you push along this line, along this side, it will move in and out. It can turn about that point. We call it hinge, line of action. The distance from here, where you are applying the force, to where you have axis is called perpendicular distance. Now, the moment of a force about any point or axis is the turning effect of the force about that point. And it is equal to the product of the force and the perpendicular distance of each line of action from that point. Now, look at moment of force equals to force times the perpendicular distance, and it is measured in Newton meter because force is in Newton and distance is in meter. You have Newton meter. Now look at this diagram. Let's say this is the point. At point C is where this ruler is being pivoted or axis. And you apply your force along this line. The distance of the force from the point of axis times the force will give you the moment of force about that point. You can see here our moment of force equals to force times distance. But when you are also applying your force at an angle theta, look at it here, theta, that means you have to find the distance. You resolve vertically downward, which is F sine theta, or you form a triangle here, then you find the distance from here to here, which is FD sine theta. That is the moment when the force is applied at an angle. Now, example. Calculate the moment of the forces of the two men. Look at. This is where it has been pivoted. This is the first man. The distance from this point to this point is 1 meter. This is the second man. The distance from here to here is 2 meters. To find the moment of this man about this point is equals to 1,000. That is the force. You can see the force is acting downward. This man too, the force is acting downward. Now, the force of this man, you can see, is the weight of this man, but it's acting downward. That means the force times the distance of this man from this middle point equals to 1,000 Newton meter. Now, the moment of the second man equals to the weight of the man, which is 500 Newton, times the distance of this man from this point equals to 1,000 Newton meter. You can see both of them are stable on this plank because their forces, their moment is balanced. That is 1,000 on this side and 1,000 on the other side. That is how to calculate moment. Now, before we can calculate our moment, there are some conditions that need to be met. which we call the condition for equilibrium under action of parallel coplanar force. Now look at, as these men are, you can see they are in a state of equilibrium because nothing is moving. That plank is not rotating, it is balanced because their moments counterbalance or cancel out. In this state, we say they are in a state of equilibrium. Now, to achieve that equilibrium state, the sum of upward forces is equal to the sum of downward forces. That is, the weight of this men is facing down. Now, the reaction of this middle point is upward. That means if you have 500, 1000 facing downward, that is, you have 1500 forces facing downward, then what is also facing up must also be 1500. We say the sum of upward forces equal to the sum of downward forces. Now, the second one, which is called the principle of moment. The sum of clockwise moment equals the sum of anti-clockwise moment. Now, look at this man carrying a ladder. A bucket of water is armed here. Then the weight of this ladder is always centered at the middle. We call it a uniform ladder because the weight is situated at the center. Now, you can see the weight of this ladder is balancing the weight of this bucket of water here. But their distance will make a huge impact on it. Now, the shoulder of this man is our pivot. We call it P. Now, look at this arrow. This arrow, we call it anti-clockwise. This one, we call it clockwise because it's moving in the same direction as our clock. That's we call it clockwise moment. And the one that is moving against it, we call it anti-clockwise moment. That means total clockwise moment about the pivot, that is this pivot, equals to total anti-clockwise moment about the same pivot. Look at it. You equate them. That is 150 times 0.6. When you multiply, it will be equals to 100 times 0.9. The same thing will give you 900. The same thing will give you 90. Sorry. That is the two conditions will be met if a particular body is under equilibrium, under the action of parallel forces. Now, look at, we can have different arrangements. Look at it. We have a plank that we have here, and we have two forces hang at the end of this plank. We have F1 and F2. The distance of F2 from this pivot is D1, D2. And the distance of F1 from this pivot is D1. Now, you use arrow to indicate your clockwise moment. That is F2 times D2. That's our clockwise moment. This is about O. That is, the middle is called point O. The clockwise moment equals to F2 D2. Now, the one that is countering it or that is opposing it is called anti-clockwise moment. About O equals to F1 times D2. Now, some of the moments. If the bar is in equilibrium, that is, when you subtract F2 D2 minus F1 D1 equals to 0, because we say they are in state of equilibrium, they must cancel out because they must be the same. Now, when you take this out, it becomes F2 D2 equals to F1 D1. That is, clockwise moment equals to anti-clockwise moment. Another one, we can have different arrangements of such. Look at, we have only F1 that is acting on this side, while F2 and F3 balance what we have here. But you can see that the distance of D1 is far more than this. But their weight will also play a huge difference there. Now, look at, we have two clockwise moments, while we have one anti-clockwise moment. Look at it here. That is F3 times D3. That is the distance of F3 from this point, and distance of F2 from this point. That is F2 D2 plus F3 D3. You add all those forces together, all those moments together. You can see we have two moments on this side. You bring them out. Then how many anti-clockwise do we have? Only one. Bring it out. Some of the moment is this. Because we said when they are in equilibrium, they cancel out. Now, F2 D2, F3 D3, this is it. Subtract F1 D1 from it, because this one is moving against or in opposite direction. Take F1 D1 out. This is what you have. This is the way we'll be calculating moment of force. Now, example. A meter rule is pivoted at its midpoint C with a vertical force of 10 Newton from distance 30 centimeters from C. At what distance must a 15 Newton force bank to balance the ruler? Now, look at, we have 10 Newton force here, then we have 15 Newton here. If you want this plank meter rule to be balanced, where should we put 15? Because you can put it anywhere. If you must find a point at which they balance, that you must look for the point where they balance. Now, we can use our condition to calculate for that. Now, this one is anti-clockwise, while this is our clockwise. We know that sum of clockwise moment equals to sum of anti-clockwise moment. Now, 10 times 30 equals to 15 times y. So y equals to 10 times 30 divided by 15. 15 here 1, 15 here 2. Y equals to 20 centimeters. That is, you place 15 Newton load at 20 centimeters to counterbalance the 10 Newton at 30 centimeters. Now, this is when we have several forces acting on a meter rule. Now, look at, we have F1, F2 facing upward. Now, we have F4 and F3 facing downward. We can take our moment about any point. We can take it about F1, about F2, or about this point. But whichever way you choose to take your moment, you must always consider the distance. Now, when we take it about point O, that is the middle of the meter rule. Now, look at, we try to identify all our clockwise and anti-clockwise moments. You can see, taking moment about O, clockwise moments, we have F1 and F3 to be clockwise moments, while F2 and F4 to be anti-clockwise movement. Just like this one moving, this one continuing the movement from here again. This one started the movement, this one continued from here again to get our anti-clockwise movement. Now look at it here. This is, and we know that from principle of movement, sum of clockwise moment equal to sum of anticlockwise moment. F1 x1 plus F3 x3 equals to F2 x3. X3 plus F4 x4. This one should be x2 and not x3 again. It should be x2. Now look at this example. A light bar is pivoted at its center, at the center, weight of 5 Newton and 10 Newton are 3 meter and 2 meter from the pivot on one side, are balanced by a weight of 20 Newton on the other side. How far is the 20 Newton from the pivot? Now look at this where it is being pivoted. Now always take note, the one on the left, on the right side here, always form the clockwise, while those one on this side form the anti-clockwise. Now how many anti-clockwise do we have here? We have 2. Always consider their distance. Now the 10 Newton is 2 meters, while the 5 Newton is 3 meters. This 20 is what we are looking for, the distance, because it's the one balancing these 2 Newton, these 2 forces. Now our clockwise moment equals to 20 times x, that is x is distance. Our anti-clockwise moment equals to 10 times 2, is it here, and 5 times 3, is it here. When you add together, it will give us 35 Newton meter. Now the bar is in equilibrium, so by the principle of moment, clockwise moment equals to anti-clockwise moment. Now what's our clockwise moment? 20x equals to 35. Now divide x equals to 35 divided by 20, which is equals to 1.75 meters. Example 2. A light beam AB sits on 2 supports at C and D. These are the support at C and D. A load of 10 Newton hang O, 2 meter from the support at C. Find the value of the reaction of the forces P and Q at C and D. Now, since the beam is light, we may ignore the weight of the beam. Now, look at this, the diagram here. This diagram here, look at it here. It has been drawn already. You have to just bring out the distance. Now, look at, if you take the moment about anyone, but here we took the moment, look at, the first thing to do is use the second condition to get for upward forces equals to downward forces. Look at it here. That is, the sum of upward forces equal to the sum of downward forces. We have 2 forces facing up, which are P and Q. Now P plus Q equals the downward forces. We have just one, which is equal to 10. Now P plus Q equals to 10. Now to now get, we now use the second condition, which is sum of clockwise moment equals to sum of anti-clockwise moment. Now from this, if you take the moment, our moment about C, that means every force we rotate about C. Now this is our clockwise, this is anti-clockwise. This is the anti-clockwise. This one is moving against our clock, while this one is moving the same direction as the clock. Now look at the clockwise moment is equal to what? 10. The distance is 2, that is 10 times 2, equals to the distance of Q from C to D, that is from here to here is 2, while from 6, while from here to here is 2. Now, Q times 2 plus 6, that is 8Q. Now, 20 equals to 8Q. Our Q equals to 20 divided by 8, which is 2.5. Now, substitute for Q in the first equation you formed to get your P, and our P is 7.5 Newton. The same way, if you take moment about D, that means every other force will rotate about D. The same thing will still apply. That will be P times 8 equals to 10 times 6. We still have the same answer. Now we move to couple. A couple is a system of two parallel and equal but opposite forces not acting in a straight line. Look at, just like I just explained in taps. Now look at, you apply the force here and you apply one here with your 2 fingers. Now this effect will bring about a turning effect, just like you also have in bicycle wheels. When we turn a tap, we are applying parallel but opposite directed force with our fingers. Now, 2 equal but opposite parallel forces have zero resultant, have turning effect or moment on the body that acts. They can produce only rotation on the body. When you have 2 but opposite equal forces, their resultant is 0, and they will only produce a turning effect like we have in our tap and bicycle wheels. Now we move to moment of a couple or torque. It is sometimes called moment of couple or torque. The moment of a couple is the product of one of the forces and the perpendicular distance between the lines of the 2 forces. Now, look at, we have one force here and one force here. To find their moment, one force is applied here, one force is applied here. That is the force times the perpendicular distance. You can easily use the one of the forces because they have the same, they are equal in magnitude. So this is how to get their moment. Force times the distance. Force times the distance. Just like what we have been doing before. Now, application of the effect of couple. 1. It is easier to turn a tap on or off by applying equal and parallel force in opposite direction. Have you tried to open a tap with one finger? You can see how difficult it will be. 2. It is also easier to turn a steering wheel of a vehicle by applying a couple with 2 ends instead of a single force with 1 arm. Assignment. Find the value of F2 and F1. Look at it here. The distance is 4 meters from the pivot, while here is 2 meters from the pivot. This one is 6 meters from the pivot. This is your clockwise, and you have 2 anti-clockwise. This is also clockwise, and this is anti-clockwise. Another example is this. You have 3 forces. One is facing up and 2 are facing down. Calculate the unknown forces X and Y. Now, when you are taking your moment about this point, that will be, this is your clockwise and this is your anti-clockwise. From there, you can calculate the value of X and Y. Till I come your way next time, we'll continue from there with the center of gravity. How you can find center of gravity. Till I come your way next time, have a great day and thank you for your time.